Okay, and welcome to lesson 3, Assemblies and Mates. In this lesson, we're going to look at assemblies and the degrees of freedom, assembly design methods, inserting parts, and applying mates to those parts. So, what is an assembly? Basically, it's where we get to, it's a document that we get to throw all our parts and group them, those parts into sub-assemblies and bolt them all together. When we throw parts or sub-assemblies into an assembly, a main assembly, we're looking at the degrees of freedom and how we could constrain those various parts in space or to each other and basically bolt them together. So with any part or assembly, sub-assembly, you've got 6 degrees of freedom, and what we'll look at is what those freedoms are. Okay, so I've got an assembly document open here, and I've just placed 2 parts in here. Now, my first part here is this cylindrical boss with a couple of steps on it, and as you may be aware, there's a little F here which is designating that this part is fixed. So in the assembly space, 3D space, it is located on the front plane, through the center of the part, the top plane through the center of the part, and the right plane on the end of the part there. So that's been fixed in place as I've inserted that component. My second part is the link arm. So my link arm, as I can see here, it's got a little hyphen which is indicating that it's actually not constrained. It's free to move. So I want to really cover the freedoms of movement. So in here I can use the move with Trider. So I've just right clicked on the part and I've moved with Trider, and so you can see this same Trider icon that's down in the bottom left hand corner of your graphics screen. You've got your RGB, red, green, blue, X, Y and Z. So 6 degrees of freedom. What are 6 degrees of freedom? Where you've got your 3 axes. X, so I can hover over the red arrow and it'll go orange, and because I'm hovering over that red arrow, I know I'm going to move in the x-axis. So I can move along the x-axis. And by grabbing that, I can actually move it a specific amount. So I can move it, what's that, coming up to 70 mil, 70.8 mil, and that's it there. X, Y, green, up and down. So I can move it up and down relative to the y-axis. And we're talking the world coordinate systems for the AutoCAD users. So we have our world coordinates over here, X, Y, and Z. X0 is the origin at the back of that part that I've fixed there. Z. The Z-axis, again, this is the 3rd degree of movement or freedom that we have with this part. So what's remaining? Well, for each axis, X, Y, and Z, we've got rotary axes. So I can turn about the x-axis. So the x is pointing out this way. I can turn in a clockwise direction. All right, is positive, and backwards is negative. All right, and that positive is based on the origin. So imagine you're standing yourself on the origin and you're looking out the positive of the x-axis. So that's a clockwise direction, moving in a positive direction value in a rotary. So I can rotate my part here quite freely, and I'll just bring it back to 0, or close enough there as for that part. So there's the 4th degree of rotation, or 4th degree of freedom, which is the rotary about the x-axis. So notice the red circle. I can find the green circle. So where's the green circle there? Hover over that, get it, it goes, highlights orange, and I can drag this about the y-axis. So this is my 5th degree of freedom. So I can rotate that around. My last degree of freedom is the blue, which is the Z. So here I can rotate around the Z axis, and I've got Z degrees, the Z axis degree of freedom. Alright, so I've just dropped that there on that. So if I quickly mate this between the boss here, anchor that, and I'm going to anchor that face to that face, make it a coincidence mate. I've now removed a certain degree of freedom. The only degree of freedom, if I right click on this, hang on, I'll exit the mate there, right click and move the triader. I can't move in the Z axis, X axis, so the red there. My degree of freedom has been removed simply by putting a constraint on the back face of the link arm and the front face of that boss step there. My y-axis, I can't move. Oh, I can. I've got a reasonable degree of freedom, and that's only really because the center of the part is slightly offset. So there I've got a degree of freedom, but it's not so much a linear movement, it's more an angular movement. Z, same again. I can't physically move in the Z axis. Alright, same with the Y, but it is allowing an angular movement. I definitely don't have any rotary axis around the Y or around the Z. So I can't move there. What I do have is rotary axis around the X. Now, it's slightly skew if only because the center of gyration for movement of the part is the part's center, not the point of reference there, its origin. So that's the degrees of freedom. Okay, assembly design methods. Basically, we've got two types: bottom-up assemblies, which is what we're going to cover in this class, and top-down assemblies, which I'll look at creating in a future advanced assemblies class. So, top-down assemblies. Basically, parts are created inside the assembly and references are created between mating parts to obtain the required design intent. In a nutshell, it allows the flexibility of parts to change as your design intent changes, and it's really good in developing and prototyping of your overall assembly design. Bottom-up assemblies. Bottom-up assemblies basically the parts drive the assembly design, and the assembly shows how all the parts mate together and interact with each other. So in a nutshell here, you create your parts and you put them inside the assembly. So we start at the bottom working on each part and we bolt them together in the assembly, and it allows us to have the parts drive the assembly, and we get to see how the assembly works and mates together. This is really good on very large projects, large assemblies there. Now, depending on your design intent, your company's requirements, there is a third, which is a blended between the two methods. But again, that is an advanced method of assembly designs. Okay, so the last bit we want to cover here is mates. Another term would be constraints, or how we're going to bolt this each part together. So there's three groups: standard mates, advanced mates, and mechanical mates. So we'll look at a few of these. Standard mates, we've got a coincidence, and as the dictionary definition is, to coincide with something, to be next to something else in space. Parallel, well, we can make things together, faces, edges together, and they run parallel. Really good for like a rack scenario where you want it to slide along and be parallel to something, but not necessarily touching. Perpendicular, similar to parallel, but we're now at a 90-degree angle. So not necessarily touching, but perpendicular to something or at right angles. Tangency, so whenever you've got something round, mating to something straight, flat, an edge or face, we can make things tangential to each other. Points aren't really tangent, they are coincident. So a point on an arc or something is a coincidence as opposed to a tangent. Concentric. Concentric, you're going to cover a lot of concentric mates together. Concentrics are usually holes. Now, you usually have a lot of bolt holes bolting each other together. Bolts and the holes that they go to, concentrics are the ones that we have there, and we'll cover a lot of that. Locking. The lock one is a good for prototyping. It's not the best one to use as an end result, but when you want to see your assembly move together, you can have another part lock and follow the other part. So it's a bit like the dog following the leader there. So you can lock another part to one another and they both follow each other in that 3D space. Last two is a distance mate. So the distance mate allows us to set a distance apart, which is really good. So we can actually specify how far apart, and the same with an angle. We can have two parts set at a specific angle away from each other there. Advanced mates, we'll look at a few of these. The symmetric mate, as you kind of guess, I love my symmetry. I love everything being symmetrical about some axis, plane, or the middle of something. So we'll use the symmetry mate. The width mate. The width mate is really good for when you've got like a slot with something else mating into it, but it's not exactly the same width. There's a bit of a gap, but the width mate allows it to run within that slot and be central to it, or offset to. You can set a little factor to it, or you can get it to play within that slot and have a bit of degree of freedom, but only within that slot boundary there. Then we can get into some of the advanced ones. We've got linear, coupler. That's something that we can follow a path or line there, really good. It is called a distance mate, but I tend to call it a distance limit. Really good for setting a boundary, i.e. like on a vise. Physically, a vise can't move an infinite distance, so you want it to work within a range, a set distance there. Same with an angle. A good example there would be a hinge. So the freedom, the angle of wrap that you want the hinge to actually physically move would be a set angle range there. The mechanical mates, I'm not going to go too far into these. Again, this would be in an advanced class, but there's a few of the mechanical mates that are available there. Alright, in summary, assemblies are where parts can be placed, fixed or mated to each other in 3D space. Parts have 6 degrees of freedom within an assembly. There are 2 design methods within assemblies, bottom up and top down. There are 3 groups of mates, standard mates, advanced mates, and mechanical mates. Mates are used to control how parts come together, move and interact within an assembly. Next we'll look at our locomotive, and we'll assemble the boiler and the axle sub-assemblies.